Okay, so here's a problem. I sketched it out of the book. So this is a frame, 10 feet tall, 8 feet wide. It's problem 953 in the book. And we want to find the horizontal displacement at B. In fact, the problem says it wants the rightward displacement, so we know which direction we're going to go. So the first thing we need to do is write moments for the real force system, and then we'll develop a virtual force system and write corresponding moments for that. So to find these moments, the first thing we'll need to do is find our reactions. So A is a pin, so I have a force in the X and Y directions, and then I have also a roller at B, and I'll find the reaction there. So I'll try to squeeze this in here. So we'll sum moments about A to start. Make sure the whole structure is in equilibrium. So that should give me a result for BY. So summing moments about A, I have BY creating positive moment with a moment arm of 8 feet. And then the 8 kip force creating negative moment with a moment arm of 10 feet. Well, that's pretty easy. So BY is 10. Okay? So now we'll sum forces in the Y direction. Make sure they're in equilibrium. So I assumed AY was acting up and BY is acting up, and that's it. So therefore AY is negative 10. That shouldn't seem too unusual to you. With this structure set this way, with this force being applied vertically, the structure basically wants to lift over and rotate, so this force is holding it down. It's kind of the same idea of a wind load pushing on the side of the structure. You really are trying to hold the structure down, keep it from rotating to the clockwise. The final calculation I need is to sum forces in the X direction. Make sure they're in equilibrium. So I've assumed AX to the right, and I have a force of 8 kips to the right. So it looks like AX is minus 8. And for the same reason. The load system is pushing it to the right, so my reaction is to the left. So let's come and calculate the moments equations in this structure. So I'll start off. Let's cut the structure somewhere we want here, and we want to look at the free body in this section, in the column section, or the other side, the whole structure. I think the column section is the easiest one. So I'll draw a free body diagram of that. And what's acting on that structure? Well, I have AY, which is 10 kips acting down, and I have AX, which is 8 kips in this direction. And then if I go up, I'll assume my moment is positive here. So this will be the moment AC, and I'll assume a coordinate system that's convenient for me. I'll just call it Y. So Y will vary from 0 to 10 and should be, tell me how my moment changes. So if I sum moments about my cut, make sure I'm in equilibrium, what do I have? Well, I have my internal moment, which I'm calling MAC. This force here is axial, creates no moment because it has no moment arm. And then I have this force here, which does create moment, which is negative. So that would be 8 kips times a moment arm of Y. So it looks like my moment in AC is 8Y. Seems to work. When Y is 0, it says the moment is 0, and that makes sense. There's no moment at the pin. I don't know what the moment will be up here, but it should match the moment that we get in section CD. Speaking of section CD, let's cut the structure there. Do you want to work this left piece or the right piece?
Right piece.
Okay, so we'll work the right piece. So I'll make a little free body diagram of that. Now on that right piece I have my reaction By, which we found was up equal to 10 kips. And that's it for applied forces. So internally I have my positive moment in CD. And I will assume a coordinate system that goes from right to left, call it x1. So x1 will vary from 0 at D to 8 feet at C. So what's the moment? Well, we'll sum moments at the cut and find out. So summing moments at the cut, making sure we're in equilibrium. The internal moment MCD is negative with my right-hand rule sign convention. And I wrote 10Y. I don't know why I did that. That should be 10 kips. Sorry about that. So the moment there would be positive. So that would be positive 10 kips. And the moment arm is X1. So it looks like the moment in CD is 10 X1. The last component in our system would be somewhere here in BD. So do you want to work this bottom piece or the left side? Yeah, I think that's kind of a self-answering question. We'll work the bottom piece. So if I drew the free body diagram for that, By is positive 10 kips acting up. And then I'll look at the moment in BD. I think you can see that if I sum moments about this cut and make sure it's in equilibrium, all I have is the internal moment BD. No external force creates additional moment. So the moment in BD is 0. I probably should have gone ahead and written that this was some coordinate y, but it really doesn't matter. This is a great result for us in this problem, because if the real moment is 0 in section BD, then we really don't care about the virtual moment at all, because the product of the real moment and the virtual moment will be 0. So we don't have to worry about it. So as I now move on to the virtual part of the problem, I'm not even going to bother to find the virtual moment in that section. I don't know if I can squeeze it in on this piece of paper, so let me redraw the system and do the virtual moment. So if I redraw my frame with the pin at A and a roller at B. Now this is going to be my virtual system. So the problem wanted the displacement at B, which is here, and it also wanted it to the right. So my virtual load then is to the right, value of 1 at B. Everybody see that? So now let's find my reactions. So I will have reactions at A in the Y and X directions, and reactions at B. Okay, so let's start. So if I sum moments at A to make sure my structure is in equilibrium, the only thing that creates moment about A is By, with the moment arm of 8 feet. Right? So what is By? 0. If I then sum forces in the y direction, assuming up is positive, making sure everything's in equilibrium, I have AY plus BY. If BY is 0, then AY is 0. So the last thing I have is I sum forces in the x direction, assuming to the right is positive, make sure they're in equilibrium. I have AX plus 1. So it looks like AX is minus 1. And that's it. Okay? So we start just like we did before. I'm going to cut somewhere here in A. I measured from the bottom up, so I'm going to do the same system. So I'll draw a free body diagram for that. I measure from the bottom up to, I called that Y. And in the same direction, I'm assuming a moment, and that'll be my virtual moment from AC. Do I have any reactions at A? I do. AY is minus 1, so it's going this direction. So what is the moment, the virtual moment in AC? So if I sum the moments about my cut section, make sure it's in equilibrium, using right-hand rule, my internal moment is positive, and the moment created by this 1 is negative with a distance of y. So it looks like my virtual moment is simply equal to y. The next system, I'm going to cut it somewhere in C to D. Let's just quickly recall that when I did C to D before, I went to the right. So I'm going to do the same thing for my virtual system. So I'll draw a free body diagram of that. And I measured it from the right. I think I called it X1. What are my reactions at B? Well, BY is 0, but I have the unit load, right? And then internally, this is the moment, virtual moment CD. So I can find that by summing my moments at the cut, making sure it's in equilibrium. This is a negative moment. This 1 creates positive moment. Oh, what's the distance? This distance is 10 feet. So that would be 1 times 10. So it looks like the moment in CD is equal to 10. Now from our previous discussion, we already know that I'm not concerned about the virtual moment in BD. So now we're ready to roll. So the displacement, so EI times the displacement at B is going to be what? So let's drop back and look at the first one. So from A to B, from A to C, this is the moment, the real moment, this is the virtual moment, and it's going to vary from 0 to 10. So I have an integral from 0 to 10 of my real moment, which is 8y, times my virtual moment, which is y, and I'm integrating dy. The next system, from C to D, this is my real moment, this is my virtual moment, and the distance from C to D is 8 feet. So I'd integrate, I'm doing it at x1, but again it's from 0 to 8. So my real moment is 10 x1, and my virtual moment is 10. So that's not too bad. I think we can do that. So the first one, this is just 8x squared. So that would be 8x cubed over 3 from 0 to 10. And then I would add to it this, which is 100x1, and I integrate that. This should be 50x1 squared, and that would go from 0 to 8. So what's that equal to? This is 8,000 divided by 3, whatever that is.
2666.
All right, hold on to that. And then what's the second one? 8 squared times 50. 64 times 50, that's 3,200?
Yes, sir.
So what's all that put together?
5866.
5866?
Yes, sir.
And that will be kip feet cubed. So now I can solve for the displacement by dividing by EI. So I've got 5,866 kip feet cubed, and now we just need to do the conversion. E for this problem was, I think it's steel, 29,000, and that's kips per inch squared. Now I for my problem was 175. Yours might be different. Yes.
You might want to round that 5866 to 5867 because it's 0.67 and 2.
Okay.
Maybe throw it all on.
How about if I just put a 0.7 in there? Is that better? Maybe that looks really nasty now. That's okay. Hopefully in the video you know why we did it. And then I need to convert that, so that's 1728 inches cubed per foot cubed. So I should get an answer in inches. What's all that equal to, guys?
I got 1.997.
1.997 inches. Now,
I got 0.667.
those are two different answers.
I got 1.997. Or 1 point, yeah, I got that.
I think I'm going with the less than 1 answer.
Oh.
This is 6,000. 6,000 divided by 30,000 is 1/5. 1/5 time. I don't know. I don't know. 2. I'm going with 2 now. I'm sticking with 2.
How about 1.997?
I think 1.997 is a pretty good answer now. I'm recanting. I like it. Okay, so now significant figure-wise, if we try to put this into our solution, what does it say? It says express your answers using 3 significant figures. So that would be, I'm willing to say it's going to be 2.00. So let's hope for the best. I'll click it over so you guys can see it. 2.00. And I don't have to put positive or negative, right?
No,
Yay!
It does like.
So it does like it.
Positive.
I didn't know that it says
So it does like it. So Mastering Engineering likes 2.00. So that seems like that's a good result.
That's because you're doing it.
So is this a good problem for the exam? I think so. It's one of those ones that you might look at initially and think, no, I'm not interested in that. But it's one of those ones that could be rigged. I mean, with all of our discussion and slowing down, the video now is only running about 19 minutes. So I think it's probably doable. So any questions about this before we stop? Okay.